start. The whole idea is to have several modular forms and construct from them in a multilinear manner other modular forms. The simplest case, two modular forms, take the product. Okay? We know that is a modular form with the weight, the sum of the weights, but there are other constructions with higher weights that involve derivatives, which are called the Rankine-Cohen brackets. So I'm ignoring all the technicalities. I don't care about the group, and I only care about holomorphicity. And we did see at some point with the meromorphic modular forms that some derivatives give you modular forms. This is something called Bool's identity. I assume that I don't encounter it. If all the weights to be positive, then we don't have to think about it. And the Rankine-Cohen brackets, which were constructed long ago, like before I was born, when my hair color tells you that it's long ago, this particular combination of derivatives of f and g, this kind of combination, is a modular form, and its weight is k plus l, the sum of the original weights, plus 2m. Now this is an old result, there's now several proofs of it. One of these proofs involves the relating quasi-modular forms to holomorphic modular forms, getting rid of the non-holomorphic issues. But I want to present a different approach to this, and this approach will also be useful for working nicely with three modular forms. Okay, so I want to get first to a proof of the Rankine-Cohen brackets in a different perspective. The proof will use vector-valued modular forms. We've seen a little bit of these in Manuel's talk, but the representation I'm putting here are not these representations that factor to a finite quotient, but rather representations that I think we saw also, this V2 that showed up there, which are restrictions to gamma of representations of the full group SL2R. Now, let's put some notation. V1 is just the standard representation acting on vectors. Vm, it's its mth symmetric power. It has dimension m plus 1. And V0 is that's the trivial representation. These are all the finite dimensional representations. And I'm going to use these representations in order to contain the derivatives and still produce modular forms without issues. So first, some technical results about this. Very well known that the tensor product of two such things is a direct sum with multiplicity 1. You start with the sum of the weights and you subtract 2 to get the next coefficient until you get the minimal one. An immediate corollary of this tensor product contains the trivial representations V0 if and only if the m and the n are the same. Okay. So, put the definition of a vector-valued modular form. It's something that behaves like a modular form. Oh, I forgot the weight. Sorry, I apologize. I forgot the weight, but you know what the weight is. But we also have this representation acting on this. And fairly obvious things to verify that if you have one representation and you have a map of representation to another representation, composing a modular form with one representation with this homomorphism gives you a modular form with the same weight as the new representations, and taking tensor products will give you the tensor product representation and the sum of units. So what happens here? What happens with derivatives? In general, derivatives of modular forms are not modular forms, but they're rather objects called quasi-modular forms that I don't want to define because I'm going to plug them into something different. But what we can do with quasi-modular forms that are holomorphic, if you want to preserve both to go back to modularity and stay holomorphic, there is a theorem I did like 15 years ago that you can take a quasi-modular form, in this case this guy, with A equals m, of depth m. You can make from it a Vm-valued actual modular form that is holomorphic, and then you don't have this nearly holomorphic things elsewhere. So these are the objects that I will construct, and for this talk, whenever I have a modular form written in a small letter, the capital letter would be this construction once we know what this m is going to be. So let's prove the Rankine-Cohen brackets. I guess you can know where I'm headed. You take the f and the g. From both of them, you construct these vector-valued modular forms with Vm, with the same m. And then, since VM tensor VM contains the trivial copy, we can form the tensor product and then take this VM tensor VM and just project onto the trivial copy. Then we'll get a modular form with a weight k plus l plus 2m, but now the trivial representation and the landing at the trivial representation is exactly what's going to give us an actual modular form without the quasi issues. And one can verify that this gives us the formula for the ranking column brackets from before. But this is the slower way to do it. The faster way to do it is observing that all these VMs are self-dual because they're the only reducible ones with their dimensions, and simply evaluate the pairing, and the pairing comes from the determinant of V1 and then the CM pairing of this, and this makes the computation significantly faster. And why is it unique? It is unique because the only way to get something with the m's derivatives is playing with the components of this capital F and this capital G, and you have only a single V0 there, and this means that you have only one way to get a modular object out of these things. Of course, when I say unique, it's always unique up to scalar multiplication. I don't care about that. So what do we do with three representations? I take three numbers, m, n, and s. I call them representation compatible. Me and Andrei call them representation compatible if their sum is even and the d, that's such that the sum is 2d, is larger or equal to all of them. This is easy to verify that it is the condition that is equivalent to the triple tensor product containing a copy of V0. If it's not representation compatible, you don't have a V0 at all. If they are, you have a single copy of V0. And using this, we can get modular forms in the following way. Take such a triple, and then you have a single operator that will increase the weight by 2d. Increasing the weight by 2d is equivalent to the combination involving sum of derivatives that sum 2d, but we impose the condition that on f we only take derivatives up to m, on g up to n, and on h up to s, and we want it to land into 2d, then there is a single way to do it, again up to scalar multiples. And how do we construct this? Of course, the 0, 0, 0 is the product we can always get. It's d equals 0, or the parameters equal 0. And there's a single way to do it. The proof is, you can guess what it is by now. Take all of these objects, the capital F, capital G, and capital H, each one with the index bounding the derivatives that we want. Take the tensor product, you land into this, and then we search for the V0. Now there are three ways to do it. The slowest one is actually evaluating the projection to V0. The fastest one is embedding, say, Vs into the other product and taking the pairing with the pairing on VM tensor Vn, and you can always have an intermediate way. The reason I'm saying it is to prepare it for quadrilinear maps that I'm not going to discuss today, but there are several ways to do it. They all give the same calculations, the same result. Just say quickly about their properties. The ranking Cohen are minus 1 to the m symmetric, immediate from the definition, and also immediate from the fact that they come through this VM pairing, which is minus 1 to the m symmetric. We can evaluate the symmetry properties of these, because then with each of them you have to interchange the index as well, so that it's going to match what's going on. Then, of course, you can't have an odd m if you want all the indices to be the same, because their sum has to be even. So if they're all the same and they're all even, then d is this number, 3m over 2. This operator is minus 1 to the m over 2 symmetric. Using a result of Min-Ho-Le that generated all the multilinear operators in some sense. Ours are the minimal ones because they're unique with the smaller bounds on the derivatives. And we can prove, to say just the simplest case, that when we fix the degree d, so we can take the derivatives only up to d, the number of operators is d plus 2 over 2. The dimension of operators that increase by this weight is d plus 1, so there are linear dependencies among them. This can be generalized to some other parameters that we want to use this to say something about quadrilinear operators, and it gets significantly more complicated. Some of them we know how to construct, but not all of them. And yeah, and I will finish here.